discovered rules that he did not like. He discovered that quantum physics was random, but he thought there was something not clear about that, and all his life he tried to find a solution to this problem and to come back to the deterministic nature of classical physics, and he failed. And now we don't try this anymore. All the experiments that we do can confirm the idea that quantum physics is inherently random.
A continuation question. Since quantum physics is a more subtle way of expressing, can we use quantum physics to actually describe all the principles of classical physics?
Yes. Quantum physics is more general than classical physics, so using quantum physics you can show that classical physics is a limit, is a limiting case of quantum physics when, for instance, if the Planck constant was going to 0, then you recover in some way classical physics. You can also show that if you have a system large enough, the quantumness vanishes and you recover classical physics. In fact, some of the experiments we have been doing demonstrate this process which is called quantum decoherence, how you lose the quantumness of systems when the size of the system increases. So in this way, classical physics is less fundamental than quantum physics because really the inner nature, properties of nature are quantum, and classicality emerges as a limit of the quantum physics under certain conditions.
To continue the same question.
Yes.
There was classical physics,
yes.
Then came quantum physics. Yes. Now we have physics that talks about string theory and all that.
Yeah.
Now, do you think string theory can explain classical physics eventually?
I think string theory is based on quantum physics. It's apply the principle of quantum physics, but it tries to describe all elementary particles as vibrations of elementary one-dimensional strings. It's a beautiful mathematical theory, but none of its predictions, which are different from the standard quantum theory, have been proved yet because they involve huge processes corresponding to energy ranges that we cannot reach for the time being. But I don't think it's in contradiction with quantum physics. It's a theory whose goal, whose dream would be to unify quantum physics with general relativity. In fact, gravitation, which is a classical theory, and quantum physics are not compatible with each other for the time being. There is no nobody has been able to describe quantum gravity in a consistent way. And this is one of the goals. If you want to become a theoretical physicist, this is one of the goals of theoretical physics today, is to understand exactly what is the link between gravitation and quantum physics.
How do you think quantum physics can change the way we look at the universe, like astrophysics?
So this is a very interesting and important question. It is related to cosmology. Cosmology is a science which tries to describe where we are coming from. How did the universe start? What happened at the time, what is called the Big Bang, and just after the Big Bang. And at that time, the universe was very small, extremely dense, and it was described by quantum theory. And as I said, quantum theory has random fluctuations in it. And according to cosmologists, these fluctuations played a very important role in the early stage of the universe. And how can we see that? In fact, a very important set of measurements are the measurements which measures the cosmic radiation background, which I talked briefly about this morning. You have radio waves coming from all the points of the universe. These radio waves are very homogeneous. Whatever direction you look at, you have the same waves, except for very small fluctuations in intensity. And these fluctuations are now mapped out with a huge precision. And you see that these small fluctuations are supposed to have quantum origin at the beginning of the universe. And they're very important because they relate to fluctuation in density of matter. And they tend to explain why the universe is not homogeneous, why you have galaxies and why you have places in the universe where matter has aggregated and how galaxies and stars and planets were created. So there is a strong connection between quantum physics, which started trying to describe the infinitely small, and cosmology, which tried to describe the infinitely large. And if you think about it, there is 60 orders of magnitude between the size of the strings you are talking about and the size of the universe. And over the 60 orders of magnitude, you need quantum physics to understand the various phenomena. There is another access to the universe which is very, very important and which has been discovered 2 years ago. It's the detection of gravitational waves. Up to 2 years ago, most of the information we had from the universe was coming from electromagnetic radiation, the background radiation, X-rays, visible light, and so on. And 2 years ago, for the first time, one has been able to detect the ripple of the space-time produced by an event occurring very far from us, the collapse of two black holes.
That's the LIGA, LIGA.
The LIGO antennas. Yeah. And this is already a tour de force in physics, because to do that, this antenna had to be able to register a change of length over 4 kilometers, a laser beam propagating between two mirrors separated by 4 kilometers, and to see a change of length which is much smaller than the size of one atom. In fact, of the order of 1 billionth of the size of a single atom. Wow. And this small variation in distance, which was observed simultaneously by two detectors, delayed by a few milliseconds, was the first signal of gravitational wave. And this again is related to the formation of black holes. And now we have other, the last event was detected last summer, right, with 3, now also the Virgo detector in Europe. And I know that in India you are building another gravitational wave antenna. It's a very important development in astronomy and in astrophysics. And again, quantum physics will eventually play a role. In fact, the lasers which are used to make this detection exploit quantum properties to increase the sensitivity of the measurement.
Who asked this question? Atisha? Did you understand the answer? Yes? Okay. All right. I have a question. Now, all the questions from the group are over. Are there any other questions?
So,
okay. I think I'm excited with you. If you get into a black hole because of time dilation, you can be both beginning and ending of the universe. Is this true?
You know, I cannot answer all questions. I am not a specialist in cosmology and in general relativity, so there are limits to what I can say. I don't know what happens if you get inside a black hole. I know the conditions are really extreme, and everything disappears inside the black hole, so I don't know. I really cannot make.
I have an answer for that, which I will give at the end of the talk. Okay. Next, please, could you mention some applications of quantum physics in dealing with the problems of the current generation, mostly economic and environmental?
Okay. In fact, I must say that most of the devices that we use in our everyday life, the modern computers, lasers, even the devices you have in a cellular phone, in your smartphones, all this is based on quantum laws. The propagation of electrons in semiconductors, magnetic resonance imaging, the use of magnetic resonance to measure small magnetic fields, atomic clocks, all this is based on quantum physics. So what would be the, so we already are benefiting from quantum physics by all the development of the last 100 years. Now, in the future, you may expect other developments. What they exactly will be, I don't know. I can give you one or two examples of dreams that people have. For instance, one has developed atomic clocks which are so precise that if you move them in the gravitational field up and down by a few centimeters, the rate at which they tick changes. This is due to a gravitational effect, general relativity. If you move them horizontally, and if there is mass densities which change, inhomogeneity in the density below the ground, you will record it. So you could use a very precise atomic clock as for geological sensing and research. Some people think that maybe before an earthquake happens, you have a slight motion of the Earth which could be registered by an array of atomic clocks synchronized with each other and looking at these small changes from one clock to the next. So this is one application which can be useful for the prediction of earthquakes. Now, you can also think of development of new sources of light using modern technologies which could be used for communication. I know, for instance, in China, they are developing what they call quantum cryptography, using sending photons to satellites and recording the light coming. So what's the problem?
No problem. He's talking to each
other. Okay. So you could use it for new ways of communicating. And I don't know what other applications would be possible in the future. Now, which application would be useful to solve some of the problems related to energy or to environmental, I don't know. Okay. It's possible.
Okay. I think there are 3 or 4 questions, which are the questions he will answer in the talks that he's going to do tomorrow and the day after. So I will postpone asking those questions. There's only one question here, which is, sir, we have heard of many inventors and discoverers, whether the idea behind the invention came accidentally, or is it that inventions can be made by working or thinking very hard?
So this is also a very interesting question, which is related to the connection between basic science and applications. What I think really the first level is basic science. You look at a problem because you are curious, you want to understand the world. And then once you have gathered knowledge, then the ideas of application come. But they come very often in a way which was not predicted at the beginning. I can give you one example, which I will describe tomorrow in more details. There are 2 inventors, Edward Purcell and Felix Bloch, working in the United States, who just after the Second World War discovered nuclear magnetic resonance. They discovered that it's possible to detect the motion of the small magnets in the atoms in a very precise way. They had no idea of the applications. They just, when they were asked in 1950 what would the application be, they said, we don't know, maybe we could measure magnetic field with high precision. 25 years later, magnetic resonance imaging was developed because in the meantime, computers came of age and high magnetic field superconductors came of age. At the time of Bloch and Purcell, they had no computers. There were no ways they could imagine that from picking up magnetic resonance, you could reconstruct images. So very often an application comes from the conjunction of several lines of research which were completely independent at the beginning. And this comes by chance. This is serendipitous. And I think this is the beauty also of research. You cannot really predict what will be going on. If you ask, if in the 1940s one had asked to scientists, I want a machine which will be able to look inside the bodies of people. I give you money and do it. There were no way to do it. And so that's why basic science should be funded without any specific application in mind, because that's the way it works. And it will be completely useless to assign precise goals without knowing what is the technology which could be developed to achieve these goals.
Thank you very much. I have a question for the audience. Somebody asked, how many of you know what is Big Bang? Please raise your hand. How many of you know what is Big Bang?
Some people.
Very few. Okay. How many of you know God exists? Raise your hand. How many of you think God created Big Bang? So, that means you don't believe God exists. Who created Big Bang? That's the question for you for the next Nobel Prize.
No, that's not a scientific question.
No, just put it there. Thank you very much. Are we running out of time?
But they have another session. I have another session.
Yeah, we have another. Yeah.
There is another session for
Yeah,
that.
we'll keep these questions for next time. Yeah.
There is another session, I think, not tomorrow, but the day after tomorrow. But thank you very much. The questions are very interesting.